Here's our second attempt at removing even number items in our list. So we're going to call this remove evens 2. The difference here is we're now going to use a for each loop instead of a while loop. So we're going to look at each item in the list. So that's what we're doing in the first line. And we're still checking to see if that item is even. So that's what's going on in the condition of our if statement right here. And if this is true, then we just simply call the remove method for that position. And then we'll just take a look at the next item of the list and so forth. So notice that in this case, we're not using the get method anymore. Instead, we're using an iterator to go through the list. Because remember, we said that the compiler is going to take a for each loop and rewrite it as an iterator if it's possible. And in this case, because we are using the collection API, we can do that. Now, this part is efficient, the fact that we're using an iterator. So that's the good news. But the problem here is that we're using the collections remove method to remove the item. And that's going to be some problems. Well, first of all, it's inefficient to use the remove method from the collection because we're doing list.remove. We're not doing the remove method from the iterator. And well, that's because we're going to have to search the item again. The remove method doesn't know exactly where it is, so it has to search the whole thing. So that's going to take linear time. And there's actually an even worse problem because we're going to get an exception. Because as we mentioned before with iterators, if we make changes to the entire collection, then the underlying iterator that we used is going to be invalidated. So if we try to run this code, it's just going to blow up on us when we try to run it. Here is our third attempt at trying to remove even numbers. So we call this remove evens 3. So the first line, we're creating an iterator. So we'd have list.iterator. We're going to store that into ITR. And then in our while loop, we're checking to see, is there still something in the list? So that's what hasNext is doing. If so, then I'm going to call itr.next right here. That's going to have me get the next node in the list or element, whether we're using arrays or a list, but we're going to get the next item in the list. We're going to check if it's an even number. And if so, we're going to use the iterators remove method instead of the collections remove method. I do want to say for this approach, it does work. We're good. We have a solution that works, and that's because after the iterator finds an even valued item, we're going to use the iterators remove method, and that is only constant time. And this is because the iterator is at the node, or at least near the node that needs to be removed. So the removing part is going to be a bit more efficient. In fact, for a linked list, this entire routine is going to take O of n time because we're just going through the entire list and we delete as we go. Now for an array list, the iterator is at the point that we need to remove. So it's pointing at the element we got to get rid of. But the problem is we still have to shift the other elements. As soon as we take out that element, we have to move everything in. So for arrays, this is still going to take O of n squared time. But at least we've seen an improvement with the linked list implementation. Now we have the running times of the remove evens method for both array list and linked list, but it'd be nice to know actually what happens when we run it on a computer. So let's ask ourselves that. What if we were to run this method on a computer? Well, we need to take a look at the execution times for both the linked list and array list implementations. So let's suppose we do this for the linked list implementation. So we would pass linked list with integer as an argument. Now I should mention that these running times are probably not going to be exactly what you would get if you were to run it on your computer, but they should be pretty close. So let's say our list has 800,000 items. It should take around 0.039 seconds, somewhere around there. Pretty fast. Now let's say we were to up this up a little bit. Yeah, I know I said up this up the size of the list. So let's say we were to double it, where we have 1.6 million items in the list. It should take around 0.073 more or less to run the method. So it seems like this is linear growth, which makes sense because with the linked list approach, it should take O of n time. So it looks like the execution times do match what our O notation said. Now let's suppose we were to pass the array list implementation for our list. So we would pass array list integer as an argument. Well, if we have the same size list for 800,000, it's going to take around 5 minutes. So that's a lot longer than the 0.039 seconds that we had with linked list. Now, what would happen if we doubled that? Well, if we went to 1.6 million, it would actually take around 20 minutes. So it's going to take 4 times as long, even though we only doubled the size of our list. So this does seem like it is pretty much approaching quadratic growth, which makes sense because with the array list implementation, it was taking O of n squared time. So we see here from an empirical standpoint, or at least what we mean by that, mean from timing the executions on a computer, that the linked list approach is a lot more efficient than the array list approach. We'll now finally get to the list iterator interface that we mentioned earlier. So if you remember, we talked about this list iterator interface, and this actually extends the functionality of an iterator for lists. So let me show you the actual code for this. So we said before, it's called list iterator. It's an interface, and it does extend the iterator interface. So we do inherit everything from the iterator interface, but we also have some additional methods in here. So we have hasPrevious. We also have a previous method, and then we also have 2 void methods. We have an add method, and we also have a set method. The previous and hasPrevious methods allow us to traverse the list from the back to the front. For arrays, this is very easy to do because we have the index. For linked lists, remember that we're using a doubly linked list, which means we do have those previous links, so we can traverse in the opposite direction. The add method just clearly adds a new item into the list at the current position. Now, what do we mean by current position? Well, the way we can think of this, we can actually abstract this by viewing the iterator as actually being between 2 places. Specifically, we can think of it as being between the item that would be given by a call to our next method, and then also between the item that would be given by a call to the previous method. So what we're saying here is at any point in the list, we can think of the iterator as being intentionally between 2 items in our list. Let's show an example of this. So let's say we have our list here being 5, 8, 14, 6, and 9. So the normal starting point here would be before the 5. So our iterator would actually be before the beginning of the list. So in this case, if we were to call next, it would return 5 because that would be the next item in the list. If we were to call previous, it would actually be illegal because there is nothing beforehand. And then if we were to call the add method, it would actually place an item before the 5. Let's say we have something like this, where the iterator is between 5 and 8. In this case, if we were to call next, it's going to return 8 because that's the next item in our list. If we were to call previous, it's going to return 5 because that's what comes before the iterator. And if we were to call add, it's going to place the item between 5 and 8. Now let's say we have something like this, where the iterator is after the 9. If we were to call next here, it would be illegal because we're at the end of the list. There's nothing that goes afterwards here. Now, if we were to call previous, it would return 9 because that's the item that comes before the iterator. And if we were to call the add method, it would place the new item after the 9, or it would add it at the end of the list. We need to mention one more thing about both the add and the set methods. So the add method does take constant time for a linked list. So that's great, but it is expensive for the array list. And I think we mentioned this several times, but it's just worth reviewing, worth repeating. With the array list, we have to shove all the elements. For a linked list, we just have to change a couple of links. Now for the set method, it does change the last value that is seen by the iterator. So remember, the iterator has some current position. So whenever we call the set method, we're going to change whatever that item is. Now this can be very convenient if we were to use the linked list implementation. Just to give an example, what we can do is we can use the set method to subtract 1 from all the even numbers in a list. We can traverse the list. If the current item is an even number, then we can call the set method to decrease it by 1. Now imagine trying to do this without the set method. This would be really hard to do for linked lists because we didn't have a way to directly access each of these items. We would have to go through the iterator, and trying to change it without the iterator, that would be pretty difficult. You'd probably have to search the entire list and it would get really messy. So using the iterators for linked list is very useful for us.